Good morning, students. Welcome to the today's class. Today we would like to discuss about lecture number 3 in unit number 3. So we talk about the design rules. In this class. Okay, what we have seen in the last class, let us recap. So we have seen that realization of the circuits. Okay. So realization of circuits with the help of NMOS technology, with the help of NMOS technology and CMOS technology that we have seen, right? Today we would like to discuss, and one more thing that we have seen is that the stick diagrams. Okay, stick diagrams. Okay, these are the things that we have seen in the last class. So what we have seen in the realization of the circuits. So whenever we have an idea, that idea is implemented with the help of NMOS transistors, symbolic representation of NMOS transistors, and CMOS orientation as well. Okay, then if you want to lay down your circuit in a silicon wafer or silicon chip, what we have to do, we have to follow some concepts under which we are going to talk about. We have talked about stick diagrams, right? So what we have done, whatever the essential layers that we normally use for a particular transistor, that is represented with the help of color codes, and we have drawn that circuit diagram with the help of color codes. Okay, now we have not considered anything about the width and length of any layers that we use in our stick diagrams. Okay, that means we haven't used any kind of uh, the dimensions of the feature dimensions of the transistors or maybe interconnections, right? But now, it is not possible to realize, or it is not possible to lay down your circuit, stick related circuit, into your silicon chip. Okay, that means the area is a physical quantity. Okay, so the silicon area is physical quantity. Therefore, we have to mention what exactly the layer dimensions, which means the length and width of the transistors, and the length of the interconnection is very important to identify. So in order to give the dimensions of this transistors or maybe interconnections, we are going to introduce the new concept called design rules. Design rules. Design rules. Okay, for example, normally we consider that, okay, so whenever we are forming a transistors, we have seen a green diffusion, and we are crossing the uh, green diffusion, something like this we have taken. But whenever we want to lay down your this material into your chip, so we have to mention what is the minimum width of this diffusion. So what is the minimum width of this diffusion? It should be, what is the minimum length of this what is the minimum length of this diffusion should be. That means that I should mention what is the minimum width, what is the minimum width of this material. So what is the minimum length of this material? So what we should know, what is the minimum length of the material we should know. So therefore we have to mention the minimum length and minimum widths. Okay, then only it is possible to construct your device in your chip. Okay, so therefore how do we mention these kind of lengths and widths of a particular material? That is decided by what kind of technology that you are using. Okay, so these design rules are based on these design rules these design rules are based on the technology that we use, the technology that we use. Okay, so therefore, what kind of technology that we are using for a particular transistor to translate into your chip? Okay, generally the technology in the sense the length of the transistor. For example, you consider the length of the transistor. For example, first one is uh, let us consider the different technologies. Okay, so for example, 350 nanometer technology, for example. For example, 250 nanometer technology, for example. Next, for example, 180 nanometer technology, for example, 90 nanometer technology, for example. So next to 45 nanometer technology, for example, 32 nanometer technology, for example, 22 nanometer technology, for example. These are the different technologies where we can form a transistor. So these technologies are exclusively meant for the length of the transistor, exclusively meant for the length of the transistor. Okay, the length of the transistor. So therefore, the length of the transistor, people normally call it as the technology of a transistor. What kind of technology of the transistor that we use? Okay, so for example, we considered, uh, 180 nanometer technology. So what does it mean? If I'm using the 180 nanometer technology, in the sense, the length of the transistor should be 180 nanometer. The length of the transistor should be 180 nanometer. Okay, so therefore, we have to define the length and width of the particular layer. Okay, that depending upon 180 nanometer technology. That means that we are using the design rules for 180 nanometer technology. For example, if you're choosing the 90 nanometer, then all the feature size in the nothing but the width of the transistors, the width and length of the transistors. So all these devices are depending upon 90 nanometer technology. So like this, whatever the technology that you use, for each and every technology has its own design rules, has its own design rules. Therefore, it's very difficult to understand that remembering of all these design rules for each and every technology. So a generic technology that we normally use, that is called lambda based design rules. Lambda based design rules. So what it is says that, okay, so whenever we are constructing the layer circuitry, okay, so we have to follow this lambda based design rules. Okay, and depending upon what kind of technology that you're using, we have to replace the lambda value with that particular technology. Clear? So what does it mean? For example, so let us define first what do you mean by lambda. Okay, what do you mean by lambda? Lambda is defined by, is a variable for the feature sizes of transistor, feature sizes of layers, feature sizes of layers. So the feature size is nothing but most of the cases we normally call the width of the layers only. Okay. Okay, and lambda is defined by the half of the length of the transistor, half of the length of the transistor, length of the transistor, half of the length of the transistor. Okay, that's what we can define. So therefore, lambda is defined by L divided by 2. So that we normally consider it in this way. Okay, that means that I can define all the materials. I can define all the feature sizes in terms of the lambda only. For example, the length of the particular so and so diffusion is so and so lambda. Okay, with the width of the transistor, width of the particular material is so and so. That is also in the form of lambda only. So therefore, we can define each and every dimension with in terms of the lambda only. Okay, so therefore, whenever I'm translating from whenever I'm moving from one technology to another technology, just I can replace the lambda value only. Okay, I can replace the lambda value with particular technology only. I don't want to consider it for the 3 to 50 nanometer technology individually, something like that. Okay, so generally we have to use a generic way of representing the dimensions of the features in terms of the lambda only. Clear? So that's what we can define the lambda. So therefore, whenever we are discussing about the design rules for any technology, first of all, we want to learn about the lambda based design rules. Okay, these design rules are also called scalable design rules. What we can call it as scalable design rules. Scalable design rules. That means that depending upon whenever you are changing one particular technology to another particular technology, just you can change this lambda value. That's all, depending upon the length of the particular technology. Okay. So therefore, for example, if I am considering that for example, so 180 nanometer technology I'm using. What do you remember the length of the transistor? Usually 180 nanometer. Then what is the lambda value that I have to consider? So 180 nanometer divided by 2. Therefore, that is called 90 nanometer. So the lambda value should be 90 nanometer. Lambda value should be 90 nanometer. For example, if I'm changing the 180 nanometer to 350 nanometer technology, then lambda value can be L value is 350 nanometer, and these things will be converted into different way. Generally, so up to 180 nanometer technology, so up to 180 nanometer, sorry, up to 180 nanometer technology. So these are called micron design rules and micron design rules. From 90 onwards, people are talking about nano design rules. Nano design rules. So 180 in the sense, for example, 180 in the sense, normally we can call it as 0.18 microns, 18 micrometers. So therefore, that's what we can normally consider in this way. But anyway, it doesn't mean that it's microns or nanometer, doesn't matter. But we consider that 180 nanometer normally we use. Or otherwise 0.18 microns also we can call it as any name that we can call it as. Okay. So this is all about lambda-based design rules. Let us consider the lambda-based design rules for different things. Okay. Yeah. I think better I should keep these things. Yep. Okay. So what kind of design rules? That means where the design rules that we have to consider. Okay. So lambda-based design rules for various layers. So where exactly that we have to use the design rules? The first one is we have to consider the design rule for wires. First, we have to consider for wires. The second one is transistors. Third one is contacts. Okay. So therefore, we have to learn the lambda-based design rules for wires, lambda-based design rules for transistors, lambda-based design rules for contacts. Right? So let us consider this one. So in generally, there is a communication between the designers and process engineer. Okay, normally, let us talk some little bit information here. So whenever we want to fabricate something, whatever the design that you have as a designer, you have some kind of idea about the your circuitry. So if you want to fabricate, if you want to design a chip, or if you want to fabricate a chip, there is a communication is required from the designer and the process engineer. So the process engineer. So the communication, the interaction between these two people is done with the help of design rules only. So with the help of the design rules only, these people will communicate to each other. Okay, suppose I have designed something. What is the main concentration for the designer? So as much as low area is required, how high performance is required. For that one, the spacing is required, and everything is spacing and performance is very, very important for the designer. But whereas when fabricating that one, there is some issues while design your circuitry in the small kind of area. Okay, sometimes it is not possible to do this one. We are not able to achieve the required dimensions of the transistors because there may be a possibility of short circuits and open circuits can be possible. So therefore, the process engineer will tell to the design engineer, okay, you have to follow these kind of rules. Then only I'm able to fabricate your chip, fabricate your circuitry in the given chip. Okay, then the designer will modify his circuitry according to that one, and he will again give back to the process engineer. So the process engineer will again check the design rules whether he has followed or not. Once it is done, then only he is able to fabricate the circuit in a chip. Okay, so that's what we can understand now. So let us consider what lambda based design rules we have to use for wire. Okay, okay, fine. Let us consider a simple let us consider wire. Okay, yeah, wire related design rules. Wire design rules. Okay, okay, um, okay. Let us consider a diffusion line. For example, we have a diffusion here. Okay, so therefore, so the minimum width of the transistor should be, okay, normally when you are using the colors, so you can use the green color. Okay, so you can use the green color, and then you can fill with this green color. Okay, that's fine. Otherwise, if you don't have any colors, for example, okay, then what we have to do is that the similar representation for this one is use the green color, something like this. If you know, if you don't have any green color, just you have to use the forward lines here this way, forward lines. Okay, so therefore, what is the minimum width of this device, this layer is minimum 2 lambda we have to maintain. So therefore, it is an N diffusion as we have seen in the color codes. Green is meant for N diffusion. What is the minimum width that we have to maintain? 2 lambda. We should maintain a minimum 2 lambda width. For example, sir, I don't want to use this minimum width. I'm going to use something like this. It is actually 1 lambda, for example. So 1 lambda means it is a design violation. 1 lambda means it's a design violation. Certainly, we have to use 2 lambda minimum width as well as length also. So the length and width must be minimum 2 lambda. Of course, by looking at this one, length is something like this. So this is up to 2 lambda. So it's more than 2 lambda. So more than 2 lambda, it doesn't matter. So maximum width is, maximum length is not, maximum width and maximum length is not a matter for us. But minimum value should be 2 lambda maintained. Why? Because the designer is expecting to reduce the area as much as possible. In that sense, he wants to reduce more and more length, more and more width. But as a process engineer should not allow this kind of thing because he's not able to fabricate on it, on the chip. So therefore, what he has to do, he will mention that, yes, if you want to reduce the area, you are allowed to reduce the area, with the help of width and length by only the 2 lambda. Okay, up to 2 lambda only, you have to maintain. There is no option at all. So that's the reason why we have to maintain 2 lambda in all the directions. Clear to all of you? I hope you understand. Similarly, for the P diffusion also. For the P diffusion, I'm using the yellow color. P diffusion, I'm using the yellow color. Sorry. P diffusion, I'm using the yellow color. I think, yeah. I'm using the yellow color. So what is the minimum width of this one? Generally, whenever you are drawing this monochrome color, that means that using only the same Mamul pen for example, in that sense, we have to use only spaced lines. So green color only you can use. You can use the green color only. Sorry, you can use the green color. You can write it in. So you have to use, fine. Yellow color only you have to use, but you have to use spaced lines that we have to use. Suppose whenever you have your colors, use these colors in this fashion. If you don't have any colors, of course, this is not the one. better. It's not like this. Suppose, for example, you have a black color, black ink only. Okay, then we have to use this black ink color. Okay, and you have to use forward slashes, something like this. And it should mention its size is 2 lambda. Okay, similarly for yellow color, so P diffusion. For the P diffusion, same black color, but you have to use spaced lines. This is also minimum 2 lambda we have to maintain. So as everybody knows that, what is this one? N diffusion. So this is called N diffusion. What is this is called? P diffusion. So if you have a colors, you have to follow in this way. If you don't have any colors, then you have to follow this method. Okay. Now, what is the distance between these two colors? Okay, just what is the minimum distance that we have to maintain between these two colors? Okay, so for example, one diffusion is going in upwards, another diffusion is going in this direction. Okay, what is the minimum distance we have to maintain? Because these are all the two conducting plates, and diffusion and P diffusions are the two conducting plates. So that means whenever it is very near to each other, the capacitance will form between these two. But our requirement is not like that. Both are must be maintained some distance, right? So what is the minimum distance we should maintain? So minimum 3 lambda we have to maintain. How much a distance we should maintain between the two materials? 3 lambda. It may be N diffusion to P diffusion, or N diffusion to N diffusion, or P diffusion to P diffusion. Is it clear to all of you? So therefore, the design rules are meant for, one point I want to write it here. The design rules are meant for feature size, feature sizes, that means the width and length of the transistors, and spacing. And spacing that we need to talk about. Okay, therefore here the feature size is 2 lambda we have to maintain. The spacing between the two layers must be 3 lambda. As I mentioned that very carefully, it is an N diffusion to N diffusion, P diffusion to P diffusion, or N diffusion to P diffusion also. Okay, so therefore the feature size in terms of, I can write one point here. The width should be width should be 2 lambda for diffusions, widths of diffusions. Widths of the diffusion must be 2 lambda, right? Right. The spacing between the diffusions, okay, spacing between diffusions should be 3 lambda. Please remember this, we have to remember. So further, please remember that the diffusion between the N diffusion to N diffusion to N diffusion. Okay, N diffusion. So sorry. N diffusion to N diffusion, or N diffusion to P diffusion, or P diffusion to P diffusion, whatever it may be. I hope you understand this, guys. Whenever we want to use a diffusion line for connecting from one to another, for example, you have one device is here, another device here, you want to connect it through the diffusion line. Okay, so another diffusion line is going something like this. Then you have to maintain the design rules for these two things. This we have to maintain that way. Okay, next, similarly, so for red, sorry, the red is meant for, okay, so this is for polysilicon. So we have to maintain the polysilicon also 2 lambda. So what is the minimum distance, minimum width of the transistor? 2 lambda width that we have to maintain for polysilicon. It is a poly. It is poly. Right. So, for example, if we don't have any colors, then we have to use backward slashes. backward slashes for this. So minimum width should be 2 lambda. So forward slashes is meant for diffusion, backward slashes meant for this one. It's very important to note that. For example, very near to each other, there is a possibility of going, for example, diffusion line, for example. So diffusion line is going something like this. Okay. Then normally these two are forming a transistor possibility is there. Or of course, these are all the conducting plates only. There may be a short circuit or there may be a transistor formation. There is a possibilities are there. So in that sense, we have to maintain the spacing between these two. Must minimum 1 lambda we have to maintain. 1 lambda we have to maintain diffusion. And it may be N diffusion or it may be P diffusion, doesn't matter. Okay, so the polysilicon width should be minimum 2 lambda. The spacing between the polysilicon to N diffusion should be 1 lambda. Yeah, there may be a possibility of another polysilicon also will go. There may be a possibility of another polysilicon is also can go. So therefore, in that sense, what does it mean? For example, something like this. So here we have another polysilicon. So what is the distance, minimum distance we have to maintain this polysilicon to this polysilicon? Minimum 2 lambda. Please remember. Don't confuse. Okay. So the minimum distance between these two are 1 lambda maintain chale. For poly to poly, we should maintain 2 lambda. Okay. Minimum 2 lambda maintain chale. Otherwise, there is a problem. Is it clear to all of you? Hope you understand this problem. So whenever we have two polys are near to each other, we have to maintain minimum 2 lambda. Whenever a poly and N diffusions are very near to each other, we have to maintain minimum 1 lambda. Okay. So, but keep in your mind that it may be an N diffusion, maybe a P diffusion, maybe a polysilicon. The minimum width must be 2 lambda, but the spacing will be different. The spacing for the two materials is N diffusion, P diffusion, and diffusions 3 lambda, polysilicons 2 lambda. So you have to remember these points. Okay, it's a poly. Please remember that this is a poly. Polysilicon, poly or polysilicon we normally call it as. Okay, so this is what the wires. And another one is also is there metal. Okay, so for the metal, what we have to use, the blue line that we have to use for metal. Okay, so blue line is meant for metal. So very important to note that. For the metal, what is the minimum distance that we have? What is the minimum width? 3 lambda we have to use. It is a metal 1. So metal 1. So what is the metal 1? Metal 1 is where is in the first level of like polysilicon and diffusion, something like this. Metal 2 is also there, which is above the metal 1. Okay, normally we consider the metal 1 only. So for the metal 1, minimum width must be 3 lambda. We have to maintain. Okay. So for example, we have another metal is going here very near to each other. Then what is the minimum width that we have to maintain? What is the spacing between these two that we have to maintain? What is the minimum width? So it is also 3 lambda. It is also 3 lambda. So that the minimum width for the metal 1 is 3 lambda, and spacing between the metal 1 and metal 1 is also 3 lambda. Okay. That's what we remember. For example, So vertical lines that we have to use for metals. So this is what the metal one that we write. Metal one. Metal one. So if you don't have any color, then we have to use uh, the vertical lines that we have to use in this way. Okay. So let us consider another metal 2 also. Metal 2 is actually above the metal 1. For example, if the more number of devices are there, it is not possible to connect through the metal 1 only. Therefore, we have to consider the metal 2 also sometimes. So for the metal 2, what I have to do is that 4 lambda we have to maintain. So 4 lambda is the metal 2 that we have to consider. This is for purple color that I have to use. So therefore, the minimum width of this one is we have to maintain minimum 4 lambda. Okay. So similarly, if we consider that we have a 2, for example, 2 metal layers, metal 1 and metal 2, then we have to consider here also 3 lambda. Sorry, 4 lambda we have to consider. So, but metal 1 and metal 2 does not require any kind of spacing. Why? Because from metal 1 above, we have an oxide. On top of it, we have a metal. So therefore, here, for example, if we consider the metal 1 here, for example, metal 1 is here. So on top of it, what we are going to use, so there is a polysilicon we have to, we have to use this silicon dioxide we use. On top of it, we are going to provide metal 1, metal 2. So therefore, there is no spacing is required between the metal 1 and metal 2. Okay, because oxide is making a difference between these two. Therefore, the capacitance formation is very, very small. It won't have a big capacitance is formed there. Okay, so in that sense, we don't have any spacing between the metal 1 and metal 2. Okay, so that's what we have to do. So therefore, I can write here is metal 2, metal 2. Metal 2 is also metal 2. It is metal 1. So these are the design rules for whites that we have to remember in our exam for our examination. Okay. So therefore, let us talk about the whites in the sense we normally consider. Okay, except metal 1 and metal 2, N diffusion, P diffusion, polysilicon has minimum width of 2 lambda. Okay, so therefore I can conclude here at this point. Okay, so the conclusion point is N diffusion, comma P diffusion, and poly as a minimum width is equal to 2 lambda, whereas metal 1 is 3 lambda, whereas metal 2 is 4 lambda. So this is for widths. This is for widths. What of the spacing? Whatever spacing. So between diffusions, we have to maintain 3 lambda. So sorry, yeah, between the diffusions, 3 lambda. Between diffusion to poly, we have to maintain 2 lambda. Sorry, it's 1 lambda. It's 1 lambda. And between poly to poly, it's very important. Poly to poly, we have to maintain 2 lambda. So that's it for the whites. For the whites, these are the design rules that we have to follow. Okay. Hope you understand this concept. Next, let us go for a transistor. Transistors. design rules. Transistors design rules. Okay, transistors design rules. For example, normally we talk about only the bipolar MOSFETs only, not the bipolar junction transistors. So let us consider enhancement design rules. Enhancement design rules. MOSFET design rules. Okay, so what we do here is that, what is the stick diagram for the NMOS transistor? Something like this: green diffusion and a polysilicon. What is the, when we apply the design rules for this one, what will form here? So there is a minimum of 2 lambda with transistor diffusion, minimum of something like this we have to form, right? Clear? So what is the dimension of the transistor here? So the middle point is a transistor formation, right? So therefore, actually here is the minimum width is 2 lambda we are maintaining, right? 2 lambda. Here also we are maintaining the 2 lambda minimum width of the diffusion. So what is the transistor? Where the transistor is formed? The transistor is formed at the middle of the transistor, middle of this one, right? Middle of this one, transistor will be formed. Okay, so transistor channel is formed. Okay, what is the dimensions of that channel then? Therefore, channel dimension is 2 lambda by 2 lambda. So length by 2 lambda. Okay, therefore this is, here is the 2 lambda. Okay, and here is that another 2 lambda is here. Right. So therefore this 2 lambda is about is observed at this point. Which color is, can you show this one? Okay. So this one. Sorry, it's not possible to show that one. So this one, I think, this is a 2 lambda, and this is another 2 lambda. Okay, the length and width. So therefore the channel dimension is 2 lambda by 2 lambda. Length and width are 2 lambda by 2 lambda. 2 lambda by 2 lambda. Similarly, for the PMOS transistor, for example, for the PMOS transistor, diffusion should be yellow line. It should be yellow line, and there should be red line. So therefore, what is this one now again? So yellow diffusion that I have to write here. So yellow diffusion. So it's not actually, it's a brown color, right? It's a brown, look like a brown color. So yellow color is not there, I think. So this is a yellow color. Yeah, so better. Right, this is the better. Yellow, red, yellow, and red. So that's it. So therefore, what is the here also dimension of the transistor? Is a PMOS enhancement PMOS transistor. Okay, channel dimension is channel dimension. Here also we can consider 2 lambda width, 2 lambda length. So 2 lambda by 2 lambda is the transistor dimension. So that is formed exactly at the middle of this one. Okay, so therefore this is the middle of this one. Channel is formed there. So here the length is 2 lambda. For example, the transistor, the width of the transistor is another 2 lambda. Okay, so therefore 2 lambda by 2 lambda transistor dimensions are observed. Okay, the length of the channel means from source to drain, right? So this is, for example, the source and anchor. This is drain. Source to drain is the length of this. Is the width of the PMOS transistor will be the length of the this one. So the width of the diffusion is nothing but the width of the transistor. Okay. For example, I want to have 8 lambda by 2 lambda. So the width is 8 lambda, length is 2 lambda. So how do I define the dimensions of the channel? What is the size of the transistor? How do we define the layer information in terms of the design rules according to this one? The width of the channel is 8 lambda should be there. The length will be the same. Okay. So do I need to change the width of the polysilicon or width of the diffusion? That's the question. Okay. So which one is the right choice? Length is 2 lambda only. Length is defined by what is the value? How do we define this one then? Any guess? So the length of the transistor is defined by source to drain distance. Okay. What I have to do? In this way I can do it. Okay. For example, I will do the possibilities here. The same diffusion I'm using, for example, and this line is something like this I have shown. And what will happen? And what will happen? What are the dimensions of this transistor then again? So you can see here very carefully. From here to here, you observe from here to here. This is the source, this is the drain, right? This is the length here. Here, this is called width of the diffusion. Okay. So therefore, the length of the transistor, what is the length of the transistor again here now? The length of the transistor is 2 lambda only, but width of the transistor is raised. Right? It is not the right approach. Okay. So therefore, what we do is that this is called 2 lambda. This is called, for example, 8 lambda. Okay. So therefore, length is actually the 8 lambda. The width of the channel is 2 lambda only, but is reversed. But it is reversed. What I have to do is then is that the length is 8 lambda and this is 2 lambda. Yes, exactly. Okay. Instead, what I can do is that, for example, if I consider the diffusion at this place, sorry. No, sorry. Okay. The diffusion is doing in this way. The diffusion is doing in this way. What is happening here then? This is the source. This is the drain, for example. So therefore, what is the distance between, what is the length of this one? It is defined by this one. What is the width of this one? So this one. The width of this one. So therefore, this is how we have to increase. So the diffusion is increased by that much amount of the time, that much amount. But N diffusion, P diffusion is something like this. Therefore, the length is, what is the length of this one? What is the length of this one? 2 lambda we have maintained. What is the width of this one? Defined by the P diffusion. So N diffusion. Therefore, it's an 8 lambda. So that's how we have to change this one. According to that one, we can change the dimensions of the either N diffusion or a polysilicon. Okay, fine. Now let us consider depletion mode type of transistor. Next, depletion mode transistor. So for the depletion mode type of transistors, what we have done here is that um, so normally this is how we look like. Okay, the diffusion is something like this, and polysilicon is something like this. Polysilicon is something like this. Usually it is 4:1. Okay, 4:1 dimensions that we have to consider. That means if the dimensions of the enhancement type transistor is 1 unit, the depletion type must be in 4 units. It should be okay. So 1 unit means in terms of the lambda, 1 into 2 lambda that we have to maintain, right? As everybody knows that. That means 1 unit is multiplied with what are the dimensions of the NMOS transistor? 2 lambda we have to maintain. What is the dimensions of the then this one? 4 times of 2 lambda. So what it should be now? 8 lambda is to 2 lambda. Okay, that is what the distance that we have to maintain. Okay, this is what we have to maintain the dimensions of the transistor. Okay, the width ratio is something like this. If the bottom transistor width is 2 lambda, upper transistor width is 8 lambda that we have to maintain. That means the width of the pull-up network or depletion mode transistor is 8 lambda than that of 2 lambda. Okay. Now, how do we do this one? Okay. So as I mentioned that what we have to do, I think better so what I can do is that diffusion we have to increase and polysilicon must be 8 lambda. Okay, something like this I'll do it here. Diffusion we have to consider 2 lambda. All the dimensions of the PMOS transistor is 4 times it should be maintained than that of the enhancement type. Okay, so therefore the length ratio, what is this width of this channel? The width of this channel is 2 lambda. So the length of the channel is 8 lambda. Okay, so therefore these are the length and width ratio. Okay, so therefore this is the length of the transistor. This is the width of the transistor. Okay, so therefore we have to maintain the 8 lambda by 2 lambda is something like this. Okay, so therefore length to width ratio. This is called length to width ratio. The length of the transistor should be 8 lambda we have to consider for the depletion mode type of transistor. Width should be 2 lambda that we have to consider. Okay, so therefore this is actually length to width ratio that we have to consider in case of enhancement to depletion. Okay, so with that we have to consider the transistor dimensions according to the width and length of the particular materials. Okay, and next one is last one is contacts. So where the contacts are required, generally when a diffusion line is uh, crossing metal line, for example, then automatically, I think better we have to write in this way, crossing something like this, Unless otherwise you not put a contact there, there is no contact is available between these two materials, right? For example, an end diffusion is causing another end diffusion. There is no need of contact. Okay. So both are equivalent to each other. That means without contact, the same materials will be connected together. Something like this also. For example, diffusion and the diffusion. Contact is not required, but they are connected. So, and P diffusion, contact is required. For example, we have a P diffusion, we have a metal here. So unless otherwise we have a contact cut here, there is no connection at all. Okay, so these are all connections. So therefore, contacts. These are all connected contacts, right? These are not a transistor formation, please remember. So how do we provide this contact here? For example, I have a N diffusion here. I have an N diffusion is going here. I have a P diffusion is also going. 3 lambda, minimum 3 lambda we have to maintain, right? This is the 2 lambda, this is maintained 4 lambda. So therefore, there is a contact cut is required here. Therefore, what I have to do is that then I have to take the overlap region of 4 lambda by 4 lambda. I have to take the contact region of 4 lambda by 4 lambda. This is the overlap region for the blue color. As well as the green color also I have to consider. So 4 lambda by 4 lambda green color on top of it. Okay, so therefore I have to draw something like this this is how we need to write. Blue color also I have to write in this way only. Vertical lines I have to consider. I have to take 2 lambda by 2 lambda contact cut. So I have to take 2 lambda by 2 lambda contact cut. So therefore, what is the overlap region dimension here? It is here is actually 4 lambda. What is the dimensions? Okay, I think it's not right way. Better I will do one once again. What is the minimum dimensions of the N diffusion? 2 lambda. What is the minimum dimensions of minimum width of the metal? 3 lambda. Now what I'm going to do here is that take overlap region of 4 lambda by 4 lambda. By the way, what is the size more than that of the diffusion for the metal? 0.5 up, 0.5 down. Okay, this is minimum 3 lambda. This is minimum 3 lambda. What is this minimum? 2 lambda. Okay, so what is the overlap region? 4 lambda by 4 lambda. This must be 4 lambda. That means this also must be 4 lambda. So here also, from here to here also, it is 4 lambda. Okay. So therefore, overlap region is actually overlap region mixing of two colors, blue color and green color. So green color, what is the lines that we have used? These are the lines that we have used. What is the metal? For the metal, vertical lines that we have used there, right? So we have to use a black color contact, something like this. If overlap region is 4.5, 4.4 by 4 lambda, what is the dimensions of this contact cut? What is the dimensions of this contact? It is 2 lambda by 2 lambda. That means if we take a overlap region, something like this, if we take a overlap region, something like this, I have combination of the two colors, green and blue. What is the intermediate point? It is called contact cut. This is called contact cut. So if it is 4 lambda by 4 lambda, 4 lambda by 4 lambda, okay, what is the dimensions of this contact cut then? It is 2 lambda. It is also 2 lambda. That means in all the directions, what is the value? So from here to here, it is 1 lambda. From here to here, it is 1 lambda. At the bottom, 2 lambda. That is total, it's a 4 lambda. Bottom one is 2 lambda. So therefore 1 lambda, 2 lambda, 1 lambda. Total is 4. So the contact cut size is 2 lambda by 2 lambda. Overlap size is 4 lambda by 4 lambda. 4 lambda by 4 lambda for overlap. 2 lambda by 2 lambda for contact. Contact cut. This is called contact cut. Right? Okay, so this is how we have to do the contact cut for this. So anyway, this is I want to clear this one with the help of this one. Again, this is also blue color. I hope you understand this concept. So the middle one is contact. Okay, so therefore what I'm doing here is the end effect is connected to the metal. Similar is applicable for the P diffusion also. Similarly, this is also applicable for diffusion also. Sorry, and P diffusion also. For example, P diffusion you are considering here. Metal I want to connect it there. This is the minimum 3 lambda I have to maintain. But overlap region, what is the overlap region? 4 lambda by 4 lambda. Okay, this is a 4 lambda. Yellow is also required overlap region 4 lambda by 4 lambda. So therefore, it's and the diffusion is something like this. Spaced lines I have to consider. So these are all the vertical lines. So therefore, this is what we normally consider for this is what we have normally considered for diffusion. Contact cut for what is the contact cut for now here now? Black color 2 lambda by 2 lambda. Black color 2 lambda by 2 lambda. Okay. So therefore we have to take a overlap region of 4 lambda by 4 lambda. Okay, it's a mixing of two colors. Okay, so at bottom we have to write black contact cut. So its dimension is 2 lambda by 2 lambda. Same thing is applicable here also. Right? For example, I want to connect polysilicon and diffusion. Not for the transistor formation, but I want to provide a connection between them. How do we provide a connection between these two? How do we connect? How do we provide a connection between these two? Of course, by the by, N diffusion to metal to. So same thing is applicable for metal also. Okay, I think it is better to write metal also. Polysilicon to metal. For example, polysilicon, I want to write it here. Okay, so quickly I'm drawing here. Polysilicon, I'm drawing here. Metal. Metal also, I have to do it. Metal also. For example, 3 lambda. So overlap region is 4 lambda by 4 lambda. Overlap region is 4 lambda by 4 lambda. So what colors that I have to use between these two? I have to use the colors called backslashes that I have to use. For this one also it's possible to write. So, but the blue color I have to write vertically. At the middle, 2 lambda by 2 lambda. So this is also same applicable here also. So that means overlap region is 4 lambda by 4 lambda and 4 lambda by 4 lambda blue color. 4 lambda blue color. At the middle, 4 lambda by 2 lambda by 2 lambda contact cut. So therefore same thing is applicable here also. Right? These are the contact cuts. Now in this case, if you want to provide a diffusion connection and diffusion or P diffusion doesn't matter. What is the possibilities here? What is the possibility here? The first possibility is that first I have to provide a polysilicon, I have to provide a metal, and then I have to provide a diffusion. So this is the possibility is there, right? So here one contact cut is required, here another contact cut is required. This is the one possibility. The second possibility is that buried contact. So we have this buried contact. The third possibility is that butting contact. Butting contact. So these are the things are. This is a conventional method. Conventional. This is the conventional contact. So that's what we can do. Normally, the metal and polysilicon and diffusion form a transistor. That's a big problem is there. Therefore, but if you want to provide a connection establishment, then we have to use this kind of three approaches are there. Of course, the first approach, conventional approach, we have seen previously. We can do the two contact cuts there. Okay, shall we read quickly then? Contacts. I have to consider polysilicon here. Okay, sorry. Polysilicon is red color. Yeah, red color I have to consider. Okay, I have to use a blue color again. This is the blue color, and I have to use green color. The green color I have to use. Okay, so here I have to provide the connectivity, the overlap region for these two things. This is the overlap region for these two things. Okay, and blue color. On top of it, we have a blue color. On top of it, we have a blue color. Okay, so red lines are moving in the far backward slashes. Blue lines are in the vertical fashion. Blue lines are in the vertical fashion here also. Green is in the forward direction. 2 lambda by 2 lambda contact cuts. 2 lambda contact cuts. Something like this. So this is the conventional approach. But whereas in the buried contacts, so buried contact, what we have to do is that except, for example, except diffusion side, in all the directions, we have to maintain minimum 2 lambda. Except diffusion side, we have to form all the directions minimum 2 lambda. That is what we have to do it. So how do we do this one? Except polysilicon side. Okay. Okay. So what is the condition here is that except polysilicon side, we have to maintain 2 lambda distance. We have to maintain 2 lambda distance for overlap region. From the channel. So that's what we have to remember. So let us write like this. For example, a polysilicon is moving in this way. Polysilicon in this way. Okay. A diffusion is going in this direction. Diffusion is going in this direction. Diffusion is going in this direction. Okay. Now, so we have to identify that this is the channel region, right? This is the channel region, right? Okay. Now, towards the polysilicon side, the overlapped region should be 1 lambda we have to maintain. From here, the 1 lambda we have to maintain. Here also 1 lambda we have to maintain. And from here to here, what is the distance? It's 1 lambda. From here to here, what is the distance? 1 lambda. Whereas diffusion side, minimum 2 lambda we have to maintain. Minimum 2 lambda we have to maintain. So that means from towards the diffusion sides, 2 lambda we have to maintain. So here also towards the diffusion side, minimum 2 lambda we have to maintain. Okay, clear to all of you? So therefore, this is what we have to understand. 2 lambda we have to maintain. Now, what is the overlap dimension here now? It is what is the dimensions of this one? It's a 1 lambda in between. For example, this is a 2 lambda but with the 2 lambda. For example, the distance between this one is 2 lambda. This is also 2 lambda, but look like more than that of 2 lambda. But don't forget about this. It's a 2 lambda also. For example, Rasangada. So let us consider this is a 3 lambda. 3 lambda, minimum 2 lambda maintain, maximum maintain. So this is 3 lambda is 2 lambda. So for this one is 1 lambda. This is 3 lambda. This is another 1 lambda. What is the value of this one now? This one. So what about this one? This is a 2 lambda. This is another 2 lambda. This is another 2 lambda. Therefore, 6 lambda is the length of the transistor, length of the material. And what is this value? 1, 3, 4 lambda, for 5 lambda. 5 lambda is another one, right? So therefore here we have to consider the dotted yellow line of dimensions here, and we have to use a dotted cross something like this also we have to consider. Okay, therefore what is the dimensions of this one? 6 lambda is the 5 lambda is the width. 5 lambda, this will be 6 lambda. No, this will be 5 lambda, right? It is yeah, that is a 5 lambda. This is 6 lambda. Yes, 6 lambda. This is 6 lambda, right? So therefore, buried contact dimensions are depending upon the dimensions of the polysilicon and dimensions of the diffusion. Please remember that, right? So wherever it is possible, you have to do in this way only. I hope you understand this concept, right? Okay, but this is more economical actually. So this is actually the buried contact is more economical. That is the reason why whenever we have realized the NMOS inverter, we use a buried contact at the top. Okay, so not butting contact. Whereas in the butting contact, what we have to do is that we have to take the metal on top of it. Okay, we have to take a metal on top of it. 6 lambda by 4 lambda overlap region that we have to consider, and we have to put a metal contact on top of it. What we have to do? So here, if you're using the buried contact, for example, butting contact, same phenomena we can consider. For example, you take this one. It doesn't follow that kind of criteria. Okay, it doesn't follow that kind of criteria. So that means towards the polysilicon side, we have to maintain the 1 lambda. On the diffusion side, we can take any value. We should not follow in that way. Okay, so what we have to follow is that we have to take the overlap region is 6 lambda by 4 lambda, something like this we have to consider. Okay, so what is the overlap region? 6 lambda by 4 lambda dimensions that we have to consider. Okay, so better I should take this way. We have to consider the metal over there. I will take one snapshot for this. Listen. Cool. copy, and then I want to paste it here. For the sake of reducing the time, I'm doing this way. So this is how we do. What here we do is that we have to take a what is this one? We by the by, this is called poly. This is a diffusion. What we have to consider is that we have to take all these two things together, and we have to consider this is a 6 lambda. We have to maintain this is 6 lambda. Okay. What is the width of this one now? It's 4 lambda. That means it is minimum 2 lambda maintain just now. Upperwards 1 lambda, bottom one is 1 lambda. Therefore, it's a 4 lambda. So therefore, we have to take the metal contact. Okay. So what I have to do here is that I have to consider the children oxide. So we have a polysilicon here. Sorry, here is better to consider as a polysilicon here. Polysilicon. And the diffusion over here. Okay. On top of it, we have a metal contact there. Okay, we have to place a metal over there. So metal we have to provide there. Metal contact. Metal contact. So on top of it, what we have to do is that, of course, there is a possibility of overlap reason for this 4 lambda by 4 lambda, and green line that we have to consider, and then we have to place black color coated here. So what is this value is actually? So therefore, it is actually 6 lambda. 6 lambda. This is 4 lambda. So now what is the contact size then? Any guess? So here is 1 lambda is 1 lambda over there. That means 2 lambda is the one thing. And what is this distance between these two? What is the distance between these two? Okay. So that means it's 6 lambda means we have to maintain 1 lambda here, 1 lambda here. So out of 6, so 2 lambdas both and the 4 lambdas. 4 lambda by 2 lambda is the contact size. It's the contact cut. Contact cut size. We have to maintain in this way. So that means that extra metal that we have to use in this particular buried contact. That is the reason why the spacing point of view, economical point of view, budding contact is not at all advisable. So for the area point of view, economical point of view, buried contact is more than sufficient. Buried contact is more than sufficient. Okay. So these are the design rules for lambda based design rules that we have to follow in this particular structure. Okay. So with this, we have come to the end of the today's session. That is design rules for the wires, transistors, and contact cuts. Okay. And by the by, whenever it is possible to maintain, for example, something like this, we have a metal line here. We have a metal line here. This is the last point that I wanted to hear. This is a metal, 3 lambda metal. For example, more than 3 lambda is 4 lambda. I want to consider this a 4 lambda. I have considered, for example, minimum 3 lambda. 3 lambda means maximum can be anything, right? So therefore, this is actually 4 lambda. For example, I have one contact here. For example, one contact here, another contact here, something like this. Okay, so another contact is also provided here. Another contact here. So that means that here we have to consider the metal contacts there. Okay, here also we have to maintain the metal contacts there, metal contact cut. So contact cut is required here also. That means that, so these 2 points, so from this contact cut to this contact cut, minimum we have to maintain 2 lambda. There is no doubt. Okay, of course, it should be ensured that if you want to make these 2 things are very near to each other, means we have to maintain 2 lambda. So here also from this contact cut to this contact cut, we have to maintain 2 lambda. Of course, ఇక్కడ నుంచి ఇక్కడికి ఏమో 0.5 కాంటాక్ట్ ఉంటుంది, ఇక్కడ నుంచి ఇక్కడికి 0.5 కాంటాక్ట్ ఉంటుంది. Therefore 0.5 అయినా 1 కాదు 2, ఇక్కడ 1 లాంబ్డా ఉంటుంది, ఇక్కడ 1 లాంబ్డా ఉంటుంది, ఇక్కడ 1 లాంబ్డా ఉంటుంది. కాబట్టి ఇది దగ్గర తీసుకురావచ్చు. We can place it very near to each other. So what does it mean is that we have to consider in this way. So the point is that I have a contact cut here. I have a one contact here. So I have to connect another contact here also, for example. So overlapped regions are very near to each other. So therefore, we have to provide a contact cut here. Here we have another contact cut. Therefore, it's possible. This is also right. Why? Because we have to maintain the minimum distance of two. Okay, the overlap region minimum one lambda is maintained from the contact cut to overlap region. Therefore, it's minimum two is a it makes sure that this is a 2 lambda. It's already available 2 lambda. Therefore, it's not necessary to maintain the distance between the two contact cuts in far distance. It's okay if it is necessary that we have to go it. If it is very near to each other, means it is possible to place all these things are near to each other. Okay, so we stop it here today. We will see the remaining things in the next class. Thank you.